Hey, what's up, guys? This is Cheng here again. So this time, 1834 single-threaded CPU. Okay, so this one, so the description is a little bit long, So you're given like n tasks labeled from n to n zero, from 0 to n minus 1, and each task has two property. So the first one is the in-queue time. Second one is the processing time. Means that this task will become available starting from this time, the in-queue time, and it takes this processing time to finish it. And the single-threaded CPU works in such a way that so first, if the CPU is idle and there are no available tasks to process, the CPU remains idle. Okay, and if the CPU is idle and there are available tasks, right, and the CPU will choose the one with the shortest processing time, right? And so basically, if at the current time, if there are like multiple tasks available, the CPU will simply take the available tasks who has the smallest processing time. Okay, and if multiple tasks has the same shortest processing time, it will choose the task with the smallest index, right? So basically, if there are multiple tasks who has the same processing time, and then which task has the smaller index, right? In the Arduino, tasks will get picked. And once the task is started, the CPU will process the entire task without stopping. Okay, and the CPU can finish a task and then start a new one instantly. And it asks you to return the order in which the CPU will process the tasks. So in example one here, so for this one, because at the beginning, since this one will definitely the task 0 will get picked first, because this one has the smallest in-queue time, right? Basically at a current time 1, at current time 1, this is current time, right? At current time 1, we have task 0 to be picked, right? And then this one, once this task 0 is finished, we have what? The current time will becomes to 3, right? Because this one, we have a task 0, we have T0 got picked, right? So after finishing the T0, the time will be 3, because in task 0 it takes 2 seconds to finish. So at current time when it's 0, we're gonna have 2 tasks become to available, which is the 1 and 3, because both those 2 tasks have the in-queue time either equal or smaller than the current time, right? But among those 2 available tasks, like I said, like what we just saw, we're gonna pick the one who has the shortest, a shorter processing time, which is the 3, which is the 3 to 1, right? So which means that this one we're gonna pick what? We're gonna pick task 2, right? Task 2. And after the task 2, since this one takes like 3 seconds to finish, now the current time becomes to 6, right? So when it comes to 6, no, this one, the last one becomes available, right? And now this one has the shorter time compared to these 2 here, right? Because only these 2 are not executed. That's why the next one will be what? Will be the 3 one, right? 3, the T3, and then the last one, since we don't have any new tasks that becomes available, and this one becomes to 4, it becomes to 10, right? Right. So the last one is like T1, right? So in the end, it will be 12, the current time. So yeah, that's basically is, that basically it is, right? For this problem, we simply just to emulate the process. That's all we need to do. But to emulate the process, so first, first things we have to sort these tasks, because we want to know at the current time, because we need to know at each new current time what are the tasks becomes available, right? And if we don't sort these tasks, we have to scan the tasks every time, right? But if we sort the tasks by the starting time, by the in-queue time, and then we simply just need to move this cursor in one direction, and we don't have to rescan the ones we have already processed, right? So that's the first thing, which means we have to sort this task. Second one is that we have to find we have to know within the current available tasks which one has the smallest, which one has the shortest processing time, and also the index, which means that within the current available tasks we need to sort. We need to sort by the processing time and the index. So to do that, we can use a priority queue, right? Because the priority queue will always give us the smallest. If we use this one as a key in the priority queue, right, then we can always get the smallest one in the end, right? And the last thing is that there could be a case that the current time is not at the current time there's no available tasks, right? So for that case, if there's no tasks to be processed, we can simply forward this current task to the next in-queue time, right? In the unprocessed tasks. Yep, I think that's it, right, for this problem. So let's get to the coding then. So like I said, we need to sort by the tasks, right? But after sorting, we'll be losing the original index, which is also useful later on, right? That's why I'm going to add that original index to the original tasks. So we have a for I, right? In this, we have a in-queue time and the processing time, right? In enumerate tasks. Okay. So I'm adding this index. Okay, so now we have the in-queue time, the processing time, and the index after sorting. Then we do sort. Okay. So let's see, we're gonna define a few variables. So the first one is the current time, right? We start at 0, and then we have a n equals length of the tasks. Then we have answer, and then we have priority queue, right? And then we have I equals 0. Basically, this one I is pointing, right, to the next available, right, tasks. And then we just need a while loop here. So while n is smaller than n, or the priority queue is not empty, right? Because because at the beginning the priority queue is empty, and as long as we still have some tasks that has not been processed, we're gonna still do this while loop here, and yeah. So first we check, right? So first we check if there's no task to process and current time is smaller, if there's no task in the queue, right? And the current time, and there's no and the current time, right? It's smaller, right? Than the next available task, right? And then we just we forward, right? We move the current time forward, right? And I smaller than n, and the current time smaller than the task I n 0, right? Then we move the current time equals to task I n 0, right? So be careful, you know. Be careful. Also check this not priority queue, because you know if there is some, if the priority queue still have something to process, we shouldn't update this current time, because as long as we have something to be processed, you know, this current time should be updated after this after the task. Okay, and if there's nothing in the priority queue, which means if there's no no available queue, sorry, if there's no available tasks, right? And then we also need to check if the current time is smaller than the first one, because you know it could be, you know, after processing the last task in the priority queue, the current time has already been updated, uh, so that we will have like some we'll have some available tasks. You know, for example, so after the last one got popped up, got processed into the priority queue. So let's say the current time. So the current time becomes to, let's say the current time was like 8, right? So after processing the last priority queue, the last task in the priority queue, this one becomes to 12, right? So now let's say the next available tasks, right? It's 10, right? And and the current time is greater than 10, right? It's greater than 10. It means that, you know, we don't have to, we shouldn't update current time, because, you know, with the current time equals to 12, we have already find a new available, at least one available task, you know. But if we update the current time to this task, you know, the current time will be updated from 12 to 10. I mean, which is wrong, because, you know, if if the next available one starting from 10, it takes like 3 seconds to finish, right? So after processing this one, you know, the current time should become to 15, right? But if we update this one to 10, you know, this one will become to 13, which is wrong, because 10 plus 3 will be 13, right? That's why we need both of these two conditions to update this, to forward this current time. Okay, so and after that, you know, we just basically we add current, we add available, right, tags on current time before, right? Which means we're gonna do I while I is smaller than n, and the task of I 0, right, is equal or smaller than the current time, we push it into the priority queue, right? Heap queue dot heap push, right, priority queue. So remember the key we're using here, the first one is the processing time, right? Which means that it's this one, is the second element in the tasks, right? So it's task I1, right? And if this processing time is the same, we also need this index to do the sorting, right? Which is the last element in the task, and then we increase I by 1, right? So now we have included the new tasks, right, for the current time, and then we simply just pick one, right? So p processing time and index, right, equals to heap queue dot heap pop priority queue. I think here we don't need to check if the priority queue is empty or not, because we have a while loop here. You know, if the priority queue is empty, right, and then we'll always add at least one task into the priority queue. So which means that, you know, when the code reaches here, there'll always be one element in the priority queue. Okay. And then we simply update the answer first, right? We update the answers, you append this one into the index, and then we update the current time equals the processing time. Okay. And then return the answer. Right. So pick next task to process. That's it, right? And yep. So let me see here. So we have that. Okay. So run the code. Oh, in queue time. This one. Okay. Submit. Yep. I mean, as you guys can see, right? So the time complexity, obviously we have an n here, right? So the while loop is n, and if we have a priority queue, that's going to be n log n, right? So the time complexity is O of n log n, and the space is O of n, because we have the task, we have the answer, we have the priority queue. And also actually the sorting itself, the sorting here is also takes n log n, right? So that's why, and here is also n log n. Yeah, so that's it, right? I mean, it's just like a problem. You have to read the description carefully. You know, once you figure out the process, all you need to do is just find a proper data structure and then emulate the process. That's it, right? Cool. I think that's it for this problem, and thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.